From the chirping of crickets to the roar of a rocket launch, we are surrounded by sound. But have you ever stopped to think about what sound actually is? It's more than just something we hear. It's a physical phenomenon, a wave of energy traveling through the air. Just like the vast universe, the world of sound is full of wonders waiting to be discovered. These waves, invisible to the naked eye, hold the key to understanding the difference between a soothing melody and jarring noise. This is the incredible story of how we perceive the world around us through the power of sound. Think about the awe-inspiring power of a symphony orchestra. From the lowest rumble of the timpani to the highest notes of the piccolo, each instrument contributes to a tapestry of sound. But what makes these sounds so different? Why do some combinations of notes evoke feelings of peace and tranquility, while others stir up excitement or tension? The answer lies in the physics of sound waves. We'll explore the concept of frequency, which determines the pitch of a sound, and amplitude, which dictates its loudness. By understanding these fundamental properties, we can unravel the mysteries of music. Noise, often perceived as unpleasant and chaotic, also plays a role in our sonic landscape. Let's tune into the fascinating world of the physics of sound. Imagine a pebble dropped into a still pond. What happens? Ripples, right? These ripples, spreading outwards from the point of impact, are waves in action. Sound, too, travels in waves, but instead of water, it's air that's doing the rippling. These waves are created by vibrations. When something vibrates, it disturbs the surrounding air molecules, causing them to bump into their neighbors. These collisions create regions of higher and lower pressure that travel outward from the source of the vibration. Think of it like a domino effect, with each air molecule passing the energy along to the next. Whether it's the vocal cords vibrating in our throat, a guitar string being plucked, or a drumhead being struck, all sounds originate from vibrations. These vibrations set the air molecules in motion, and these waves of pressure travel to our ears, allowing us to experience the world of sound. Now that we understand sound travels in waves, let's dive into some key characteristics of these waves. One of the most important is frequency. Frequency refers to how many sound waves pass a given point in 1 second. We measure frequency in hertz, where 1 hertz equals 1 wave per second. A higher frequency means more waves are squeezing past that point every second, resulting in a higher pitched sound. On the other hand, low-frequency sounds, like the rumble of distant thunder, have fewer waves per second. Our ears are incredibly versatile, capable of detecting a vast range of frequencies. This range, known as the audible spectrum, is what allows us to perceive the rich tapestry of sounds in our world. Imagine yourself at a rock concert. The music is booming, the ground vibrates beneath your feet. Now, picture yourself in a quiet library. The only sounds are the gentle turning of pages. What's the key difference in these scenarios? It's the amplitude of the sound waves. Amplitude refers to the intensity or strength of a sound wave. We perceive amplitude as loudness. A sound wave with a large amplitude carries more energy and sounds louder to our ears, like that rock concert. Conversely, a sound wave with a small amplitude carries less energy and sounds quieter, like the hushed whispers in a library. We've established that sound travels in waves, but how do these waves reach our ears from the world around us? Imagine for a moment the air as an ocean of tiny particles. When a sound is created, it's like dropping a pebble into this ocean, causing ripples to spread outward. These ripples, or sound waves, are actually variations in air pressure. As a sound wave travels through the air, it causes the air molecules to vibrate back and forth. These vibrations are passed from one molecule to the next, like a chain reaction. The amazing thing is that the air molecules themselves aren't traveling with the wave, they are just oscillating back and forth. Similarly, sound waves create a pattern of compressions and rarefactions in the air, areas of slightly higher and lower pressure, and these pressure variations travel outward from the sound source. Our ears are incredibly intricate and sensitive organs, specifically designed to capture these subtle pressure changes in the air and transform them into electrical signals our brains can understand. The journey begins with the outer ear, the part we see, which acts like a funnel, collecting sound waves and channeling them into the ear canal. At the end of the ear canal lies the eardrum, a thin, cone-shaped membrane. When sound waves strike the eardrum, it vibrates in response to the changes in air pressure. These vibrations are then passed on to the middle ear. The middle ear houses three tiny bones, the malleus, incus, and stapes, collectively known as the ossicles. The inner ear is the heart of auditory processing. It houses the cochlea, a spiral-shaped, fluid-filled structure that plays a critical role in transforming sound vibrations into electrical signals. Within the cochlea lies the basilar membrane, a flexible structure that runs along its entire length. When vibrations from the middle ear reach the cochlea, they cause waves to travel along the basilar membrane. Different frequencies of sound cause different parts of the basilar membrane to vibrate most strongly. Attached to the basilar membrane are thousands of tiny hair cells, the sensory receptors for sound. The auditory nerve carries the electrical signals generated in the cochlea to the auditory cortex, a region of the brain dedicated to processing sound. Here, the brain performs an incredible feat of analysis and interpretation. It decodes the complex patterns of electrical signals, identifying the pitch, loudness, timbre, and location of the sound. Think about listening to your favorite song. The brain can distinguish the different instruments playing, the melody, the harmony, and even the emotion conveyed by the music. This process of auditory perception is a testament to the power and complexity of the human brain. Our ears are remarkable instruments, capable of detecting an astonishing range of frequencies. This range, known as the audible spectrum, spans from the lowest rumbles we can barely perceive to the highest pitches that border on the edge of our hearing. For humans, this range typically falls between 20 Hz at the low end and 20,000 Hz, or 20 kHz at the high end. Imagine a vast piano keyboard stretching out before you, representing the entire audible spectrum. At the far left, you have the low, rumbling frequencies, like the depths of a pipe organ or the distant boom of thunder. As you move towards the center, the frequencies increase, encompassing the rich tones of human voices, the melodies of violins, and the bright sounds of trumpets. Section 2 notes the building blocks of music. Within the vast expanse of the audible spectrum, we humans have carved out specific frequencies that hold special significance: musical notes. These notes are not randomly scattered but are organized into systems that form the foundation of melodies, harmonies, and all the music we know and love. The most common system of musical notes in Western music is the chromatic scale, which divides the octave, the interval between two notes where the higher note has twice the frequency of the lower note, into 12 equal semitones. These 12 semitones, represented by the notes C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, and B, form the building blocks of countless musical compositions. Section 3. Orchestrating sound instruments and their frequencies. One of the most fascinating aspects of sound is how different frequencies can be combined to create the vast array of musical instruments we have today. Each instrument, from the simple flute to the complex piano, is designed to produce a specific range of frequencies, giving it its unique timbre or tone color. Consider the string instruments like the violin, viola, cello, and double bass. These instruments produce sound through the vibration of strings, which are stretched tautly across a resonating body. The length, thickness, and tension of the strings determine the frequency of the sound produced. Wind instruments, such as flutes, clarinets, trumpets, and tubas, create sound by setting a column of air vibrating within a tube. Section 1. The Symphony of Frequencies, Consonance and Dissonance. Music, at its core, is a carefully crafted interplay of sound waves, each with its unique frequency. When these frequencies interact, they create a fascinating phenomenon: harmony and dissonance. This interplay of consonance and dissonance lies at the heart of musical expression, shaping our emotional response to music. Consonance refers to the combination of sounds that are pleasing to the ear. These sounds, when played together, create a sense of stability, resolution, and a pleasing blend that feels harmonious. Dissonance, on the other hand, refers to the combination of sounds that create a sense of tension, clash, or instability. Section 2. Harmonious relationships, building blocks of musical structure. The concept of consonance is deeply rooted in the physics of sound waves. When two notes have frequencies that are simple ratios of each other, they tend to sound consonant. For example, the octave, where the higher note has twice the frequency of the lower note, a 2-to-1 ratio, is considered the most consonant interval. Another highly consonant interval is the perfect fifth, where the ratio of frequencies is 3-to-2. These simple ratios create sound waves that reinforce each other, resulting in a stable and pleasing sound. Section 3. Dissonance. Adding spice to the musical palette. While consonance provides a sense of stability and resolution in music, dissonance is equally important. Dissonance injects tension, drama, and emotional depth into music. It creates a sense of anticipation, urging the listener towards resolution. Think of it as the spice in a culinary dish. A little bit can go a long way, adding complexity and interest. Composers use dissonance strategically to create a wide range of effects. A sudden dissonant chord can evoke feelings of surprise, fear, or excitement. Section 4. Scales, mapping the musical landscape. Over centuries, musicians and composers have developed systems for organizing musical notes into scales. Scales provide a framework for creating melodies and harmonies, defining the specific notes that sound consonant or dissonant within a particular musical system. The most common scale in Western music is the major scale. The major scale is constructed using a specific pattern of whole and half steps, the intervals between adjacent notes in a scale, resulting in a bright and cheerful sound. The minor scale, on the other hand, uses a slightly different pattern of intervals, creating a darker and more melancholic sound. These scales, and the countless variations that exist across different cultures and musical traditions, serve as roadmaps for composers, guiding their choices of notes, chords, and progressions. They provide a framework for creating the vast and diverse world of music we know and love. Music has an extraordinary power to evoke emotions. A soaring melody can lift our spirits, a mournful tune can bring tears to our eyes, and a driving rhythm can compel us to move. How do mere vibrations elicit such profound responses? The answer lies in the interplay between sound and the brain. Over millennia, we've evolved to link sounds with emotions. A baby's cry triggers urgency, while laughter brings joy. Music amplifies this connection. Through melodies, harmonies, and rhythms, composers evoke a spectrum of feelings. A major key conveys happiness, while a minor key evokes sadness. While music can enrich our lives, noise pollution has become an increasingly pervasive problem in our modern world. Constant exposure to loud, unwanted sounds can have detrimental effects on our physical and mental well-being, leading to stress, sleep disturbances, and even hearing loss. Imagine living near a busy highway, a construction site, or an airport. The relentless roar of traffic, the hammering and drilling of machinery, the deafening thunder of airplanes taking off and landing. These sounds can create a chronic state of stress, making it difficult to relax, concentrate, or get a good night's sleep. Prolonged exposure to noise pollution can also lead to hearing loss, a condition that affects millions of people worldwide. Loud sounds can damage the delicate hair cells in the inner ear, leading to gradual or sudden hearing impairment. This can have a profound impact on our ability to communicate, enjoy music, and engage fully with the world around us. Just as noise can harm us, music has the remarkable ability to heal. Music therapy uses sound to improve health, addressing physical and mental conditions. It stimulates brain activity, improves motor coordination, and reduces anxiety and pain. Rhythmic patterns retrain the brain while emotional content motivates patience. From the quietest whisper to the grandest symphony, sound is essential to the human experience. We've explored sound waves, the ear's workings, and the brain's power to interpret sound. Frequency and amplitude shape our perception of pitch and loudness, creating the music we love and the noise we endure. Music evokes emotions, connects us, and promotes healing. Sound is more than a physical phenomenon, it's a fundamental human experience. So, let the music wash over you and appreciate the dance of science and art. If you like this content, please comment, like and subscribe.